In this video, we're going to go over the answers to the 3 practice problems that are on the second page of your water potential notes. So here are the 2 formulas for water potential. So the total water potential is equal to the sum of the solute potential and the pressure potential. And this is a formula for calculating the solute potential, negative ICRT, where I is the ionization constant. It refers to how many ions are formed when a substance is dissolved in water. C is a molar concentration. R is a constant. We always use that number. And all of these units become useful for canceling out all the other units other than atmosphere, which is equivalent to 1 bar. So 1 atmosphere is equal to 1 bar. That's the pressure unit for water potential. Finally, T is for temperature in Kelvin. And this is one step that many students often forget to do. You have to convert degrees Celsius to Kelvin by adding 273. So let's get to the first question. Number 1, calculate the water potential of the solution in an open beaker that has 0.7 molar glucose at 25 degrees Celsius. The fact that the solution is an open beaker means that the pressure potential of the solution is 0. This always applies when we're dealing with a solution contained in an open beaker with no lid. Okay, so let's go ahead and calculate the solute potential and the pressure potential. So we already said that the pressure potential must be 0 because this is an open beaker. And now the total water potential just becomes solute potential, which is negative ICRT. So ionization constant of glucose will be 1 because glucose is a molecular compound that does not ionize in water. C is the molar concentration, 0.7. R is always a constant, 0.0831. And finally, T is the Kelvin temperature, so 25 plus 273. So you multiply all of these 3 numbers in your calculator. You get negative 17.3 bar for your answer. Okay, now let's get to number 2. So potato cores were placed in 0.34 sodium chloride in an open beaker at 22 degrees Celsius. If there is no net water movement, what would be the water potential of the potato cores? For this problem, let's start by sketching out the situation. So we have an open beaker. We have 0.34 molar sodium chloride solution at 22 degrees Celsius. And we have potato core right there. And now, the information that we're given here is about the solution that's on the outside. But what the problem is actually asking us to calculate is the water potential of the potato core itself. So, but there is a key phrase here, right? So it says that there's no net water movement. This means that the whole system is at equilibrium. What this means is that the water potential of the potato core is equal to the water potential of the solution that's sitting on the outside. That's why no net water movement is occurring. So by calculating the water potential of the solution, we're automatically calculating the water potential of the potato core. So that's what we're going to do. So again, the water potential is equal to solute potential plus the pressure potential, but we're dealing with an open beaker, so the pressure potential is equal to 0. So we just do negative ICRT. Ionization constant for sodium chloride is 2 because sodium chloride will ionize into sodium and chloride ions. C is the molar concentration, which is 0.34. R is 0.0831. And temperature in Kelvin is 22 plus 273. So put all of these into the calculator. And you should get negative 16.7 bar. Okay, so second question was also easy enough. Let's go to number 3 then. So at 20 degrees Celsius, zucchini core with a pressure potential of 3 bar is in equilibrium with the surrounding 0.4 molar sucrose solution in an open container. So this is at 20 degrees, and here is the zucchini core. Now, one thing that we know about this is that the pressure potential is given. It's at 3 bar. Now, what the problem actually asks us to calculate is the molarity of sucrose inside the zucchini core. So this really is a two-step question. Again, it says that this is an equilibrium, which means that the water potential of the solution that's on the outside of the cell is equal to the water potential of the zucchini core that's submerged in, right? So what we're going to do is we're going to calculate the water potential of the solution first. That's step number one. Then we're going to use that to backtrack and find the molarity of sucrose. So let's do step number one first. Again, water potential of the solution on the outside. That will be solute potential plus the pressure potential. But since we're dealing with an open beaker, that becomes 0. So that just becomes negative ICRT, where I, for sucrose, is just 1. It's a molecular compound. The molar concentration is 0.4 molar. R is 0.831. And temperature, so 20 degrees Celsius, so 273 plus 20 will be 293 Kelvin. So that gives us negative 9.74. So again, calculating this gives us the water potential of the zucchini, the total water potential of zucchini, right? So that's negative 9.74. And again, water potential is calculated by solute potential plus pressure potential. In this case, pressure potential is given. It's equal to 3. So that means the solute potential of zucchini is equal to negative 12.74. So what I did there is I just solved for solute potential by subtracting 3 from both sides, right? So that's solute potential. And that's equal to negative ICRT. So let's plug into that formula. So negative I for sucrose, again, is just 1. It's a molecular compound. C, that's the molar concentration that we need to look for. That's our X. That's our unknown. R is 0.0831. And finally, T is still at 293 Kelvin. So now this is a simple algebra where you're solving for this C right there. Okay. And I'll let you figure that out. It's a simple division, right? You should get 0.52 molar sucrose for the zucchini core. That's how you get the answer. So if any of these solutions didn't make sense, please go back and rewatch the video and be sure to bring any questions to class.